All right. So we're going to finish 3.2. We're nearly done. We just had one little problem left to do, and that problem is a subtraction problem in another base on our last slide. Now, just a reminder, we did an addition problem in another base last time, and I showed it to you in a couple of ways. We talked about the fact that this number line idea will help us. So writing out sort of several of the digits into the two-digit numbers into the certain bases. The certain base you're working in might help you to do the addition. You can do it with lattice, you can do it with standard algorithms. There's not usually any directions on those. Of course, if there are specifics, use those. We're going to do a subtraction one. And we're going to start out by writing it just like we did subtraction back in first and second grade. And these are all in base 3. And I'm going to show you at least two ways of doing the problem, okay? So the first thing I'm going to show you is I'm going to show you the standard algorithm for subtraction in base 3. Now, we start on the right-hand side, we subtract just like, you remember doing back when. So if we say 2 minus 0, we get 2. And we're happy just fine with that. But what do you notice happens next? You have to borrow, right? I've got a 0 on top, I've got a 1 on bottom. I can't take 1 away from 0, so you have to borrow. What happens when you borrow in base 3? You borrow 3. Everybody with me? In base 10, you borrow 10. So please don't borrow 10 because there's not 10 in the place over here to borrow from. There's only 3 there. Every place value is worth 3, or 3 more than the place before. So when we borrow, the problem is I can't borrow, and then this one's even worse because I can't borrow from nothing, so I have to come back over here, right? So if I take this 1, the 1 will turn into a 0, and then I'm borrowed from that place value 3 right now. Okay? But I need numbers 1 more over. I'm not done. I still need to get back over to the second place. So this 3 will become a 2, and this 0 will become a 3, because I'm borrowing 3 in base 3. There's not, but neither is there a 10 in base 10, and we write 10 down just fine in base 10, don't we, when we do this? Yeah. So we're using our digit for their number, and there isn't one of those digits, but neither is there a single digit, like 14, but we sometimes will write it when we're subtracting. I'm going to show you another way, too, if you don't like this. Bear with me. All right, so then you can subtract now, right? So we've got 3 minus 1 is 2, and then 2 minus 1 is 1, and this is base 3. So your answer is 1, 2, 2, base 3. Yes, Addie?
If those weren't zeros, and say it was 1, do you add 3 plus 1 and then it's 4?
Yes, we would. Just like with us, right? We would add 4 plus 10 to make it 14. Yes. All right, I'm going to show you one other way to do this one, though. Okay, so we're going to do that equals addition algorithm. And since you haven't seen it since Monday, this is a good time to see it. Okay, it's called equals addition. Do you remember what the goal was in equal addition? Not borrow. The goal is to do things to the numbers so that we do not have to borrow. Okay? So right now, the 0 in the 1's place is just fine. You don't have to borrow or anything like that, so there's nothing going on there that makes you have problems. But the 1 in the second place value, which is the 3's place, that one's got problems, right? What would I have to add to a 1 to get it to turn into a 0? 2. That's right. Because what is 1 plus 2 in base 3? It's 1, 0, right? Just like when we say, what is 8 plus 6, or 8 plus 2 in our base? What's 8 plus 2? 10, right? It turns that placeholder into a 0, and it moves it over, it rounds it up, it lets us carry. Okay, so what I'm going to do right here first is I'm going to add the number 2, 0. And notice I keep saying, even like when Haley said, she said 10. I keep saying 1, 0 because it's not really 10. It's a 1 in the 10's place, or in the 3's place, and a 0 in the 1's place. So I'm going to say 1, 0. So I'm going to add 2, 0 to this number. But if I add 2, 0 here, I have to equally add it up here. All right, so let's do that. So I have 1, 0, 0, 2 plus 2, 0, which is 1, 0, 2, 2, right? And then what happens here? What happens when I do 1, 1, 0 plus 2, 0? We already said the whole goal was that it turns these both into zeros. And I get 2, 0, 0. Can I stop here?
No.
No. Why not? Because I would still have to borrow. And the whole purpose behind this method is no borrowing. So what would I have to add to 2, 0, 0 to not have to borrow? 1, 0, 0. And if I do it to the second number, I'm going to do it to the first number. All right, so if I add 1, 0, 2, 2 to 1, 0, 0, what do I get? 1, 1, 2, 2. And if I add 2, 0, 0 to 1, 0, 0, what do I get? Good, 1, 0, 0, 0. You guys are getting the hang of this, awesome. Can I subtract without borrowing?
Yeah.
Absolutely. What do I get?
1, 2, 2.
1, 2, 2,
Base 3.
base 3. Same answer, different method. Yes.
Can you explain where you got the 2, 0 in the very first step?
This one, yes.
Right.
My goal was to get this number right here to become a 0. And if I add the number 1 to it, 1 plus 1 is 2, that doesn't help. But if I add the number 2 to it, 1 plus 2 would be 3 in our system, but 3 in base 3 is represented as 1, 0. So it allows me, if I add this 2 and this 1 together, to get a 0, and then that 1 that we would have gotten would add to the original 1 in the first part of the number to become a 2. That's what's happening. In other words, let me draw it out this way too, might help, I don't know. If I add 2 plus 1, I get 3. There is no 3, so I put down a 0 and I carry a 1 because 1, 0 is the number in base 3. And then I'd have the 2, 0, 0 there. Any other questions on this one? All right.